Hello everyone, welcome to another video where today I would like to talk about Flatzoid and error or measurements, or technically it was triggered by the recent debate against critical think. Now I will talk about this later, just as a preface. Critical think does not need anyone to defend him. I think he did a pretty good job of defending himself, considering especially that he has never been in a debate before. But I would like to add a couple of things added to show that Flatzoid really has no idea about measurements. This has been such a striking experience. I have to talk about it. There is no other way. So, first of all, a little bit of an overview. First of all, let's talk about mistakes. Then let's talk about uncertainty. Then talk about accuracy and precision. Then talk about a real-world example of my own data, and then we will be talking about a few claims that Flatzoid has made. So let's go. Mistakes, first of all, they could be part of a measurement, but of course they should be avoided. There are two types of mistakes in a scientific experiment. There are systematic mistakes, where the direction of the mistake can be known. So for example, let's say you watch the time of some physical process. However, you later find out that your stopwatch is for some reason off by 1 minute. So this is a mistake, of course, and it lowers the overall plausibility of the experiment, because if you made this mistake, you might have as well made some others. But it can be corrected systematically. So you can say at the end, when your data doesn't quite add up, for example, with a scale, when the scale for some reason just measures 25 grams too low at all times. So if your experiment doesn't make sense and you find this out later, you can be like, there it makes sense, and you then subtract 25 grams from all of the weights, right? This can be corrected. Then there are so-called fatal mistakes. Those cannot be corrected. So, for example, the direction or the magnitude of a given mistake is unknown. So, for example, you would like to measure the current, but so you would like to measure voltage, but instead you, on accident, set the multimeter setting to current, and you record this as your voltage value, and later on you have no way of knowing what the voltage actually was. This cannot be corrected. Right? These should be, of course, avoided. This is just a little pretext, just so we know what we're talking about when we're talking about mistake, error, and uncertainty. They all sound similar, so let's to get a disambiguation. So then uncertainties, or here abbreviated as UC, there are internal uncertainties. They come from the measurement apparatus, and they apply to single values. So, for example, the scale of an analog voltmeter. How exact can you read the value of the multimeter? And how exact can a device measure? The producer of multimeters, they state this in the fact sheet. They say we can only measure, for example, when we measure down to millivolts, we can only measure, for example, as precisely as 1,000th of a volt, 1 millivolt. We cannot go anything better than that. So you need to add plus minus 1 millivolt in this case, for example. And then there are external uncertainties. They come from the spread of values. So if you measure the same thing 10 times, you get a certain spread within these values. This has to do with the measurement apparatus being not exact, and some small conditions changing, and so on and so forth. So this only applies to a group of measurements. So for example, you take 20 temperature measurements, and in this group of measurements, the temperature range goes from 30 to 33 degrees Celsius. So this is a certain spread, and the spread, of course, introduces an uncertainty, because you can say, well, it's 31.5 on average, plus minus 1.5 degrees, for example. Okay, let's quickly also talk about accuracy and precision. I would say precision is how close your measurement values are together, and accuracy is how close they are to your target. So, for example, here you have low accuracy and low precision, so they are pretty scattered and they are not exactly where they should be on the target. Here you have high precision, but still low accuracy. And for example, here you have high accuracy and high precision. Not that this is important, but these are really the basics of measurement, so you should have heard about this one time, because Flatzoid clearly has no idea about how to measure things, so I need to make this extremely plain. This is also to be made extremely plain for people who just haven't ever measured things in a scientific context, which is completely fine. Take this as a little introduction on how to measure things in science. So let's get a real example, a small little test with my own data that I'm currently collecting for my physics master thesis at a particle detector. So let's say we have our particle detector measured 104 counts of a given particle over 200 seconds. So the internal uncertainty due to the detector, we know this very well. And at the range of 100 counts, it is around 10 counts, plus or minus, right? So over 200 seconds, my result would then be 104 plus minus 10 counts. So, right, in 4 seconds. I don't know why there's 4 seconds there. I'm sorry, there should be 200 seconds. I apologize. So I can't make a more accurate statement about my counts. 104 plus minus 10. That's it. Now I measure it a second time, and now I get 97 plus minus 10 counts. Now, question to everyone who wants to learn about uncertainties here: are these two values in agreement? We have 104 plus minus 10, and we have 97 plus minus 10. Do these values agree? Particularly, this question is addressed at Flatzoid. Do these values agree? Let's say you have one here, and you have one here, and this is the data point, and this is the height of the uncertainty. You have two data points here. Are those two data points in agreement? And the answer, of course, is yes. If you go with the highest uncertainty, with 97 plus 10 is 107, which is in the range of this first uncertainty. These two values agree with each other. In a scientific context, we would say that the particles detected over the 200 seconds stayed the same within uncertainty. Within uncertainty, of course, is important. If my next measurement value was 85 plus minus 9, well, then we would, of course, have to think about things, because then there's a decreasing pattern visible. But just from these two data points, they are the same within error or within uncertainty. Another real example, this was from one of the lab classes that I did in my bachelor's course. I have absolutely zero idea, I must admit, what we did in this experiment, because there's a position on the marked scale. I have no recollection of a marked scale in centimeters, and there's a force applied to Newton. So I guess we were testing Hooke's law. So we were pulling down on things. So we pulled down from 4 centimeters to 2 with roughly 10 newtons of force applied. I do, however, remember that reading the scale off with this stupid thing that we used for it was notoriously difficult, which I think was the point of the exercise. So we had to estimate our own error while reading off the data. And I recall that with this thing here, there was a little bit of vibration, so we gave it a higher uncertainty. Regardless, these are my measurement points, the blue stars here, and the bars here again are my error bars. So would we say that this is okay? Yes, we're still fine. Why are we still fine? Well, first of all, we neglected the mass of the hook and the string we used to measure this thing, and we also never measured any kind of temperature, humidity, and air pressure, by the way, Flatzoid. We never did that, but we're still good. This is because your data is not expected to always be where it should be. It has a scatter for a good reason. If we assume that our data points will be distributed in a Gaussian way around the value we expect it to be, around 20 to 30% may be outside of there with simple single uncertainty. This is a little bit more advanced than the basics we're doing here. What I'm trying to say is, if only 90% of your data agree with your theoretical prediction, you can either think about increasing the error that you have if you find a good reason for it, or you can say, well, nothing's perfect, measurement conditions are never perfect, we could have made a mistake, and so on and so forth. The equipment could have been faulty, things like that. Partially faulty, for example. But as long as you don't have a systematic trend in it, this is still fine. We can easily argue, I mentioned that earlier, that there was a little bit of a wobble in the Newton meter there, and this is why we gave it higher uncertainty. Turns out we probably should have given it a little bit higher uncertainty than we did. So I changed the data of the thing. For example, if it would look like that, well, that's bad. Only two measurement points. Let's say we give ourselves that one and this one agree. The other ones seem to be out of order in no given way. Well, this would be a problem. You could not make a scientific case to save this hypothesis that you're doing. You would have a really, really hard time unless you show that your equipment was completely faulty or that some mistake happened, for example, a fatal error, then you could repeat the measurement. Note that here, if you fit a line through it, you will get very close to the theoretical expectation, by the way. Didn't say that before. So this would be bad. All right, and now I would like to go into the videos. I've prepared a whole bunch of videos, and I would like to start, surprisingly, by correcting Critical Think, although I think he held himself pretty good.
Random effect cannot produce a... And so? It's a random effect. A random effect cannot produce a correlation. That's science for you, Flat.
That, unfortunately, is wrong, Critical Think. Don't get me wrong, I'm 100% on your side of this discussion, and I've only briefly looked at your data, but I am impressed with what you did. Critical Think's claim, a random effect cannot produce correlation, unfortunately, is wrong. It is just extremely unlikely to produce correlation, but possible. Take our example again, the position on the marked scale and the force applied. Randomness could have caused these values. It's just very unlikely that they did. So now I wondered myself, how unlikely would that have been? So I took a little time and simulated 7 measurement points with 0.2 centimeters of error. And it took me, this is completely manufactured data. This is only random data within the range of 2 to 4. All of these values are random, all of the blue ones, and they fit pretty nicely. But it took over 500,000 tries for these 7 points to fit within the theoretical expectation with only 0.2 centimeters of error. So technically, again, it is possible. A random effect can cause correlation. It's just very unlikely to do so. And the more measurement points you have, the more unlikely this becomes to the point where there is no reasonable way of doing so. Of course, science is repeatable. So if you repeat it and you find some completely different argument, well, maybe you could find a way to say it was random. I completely give it to you within the precision that you do it. It would be ridiculously unlikely for that to happen, but technically it's still possible. Now let's move on to Flatzoid's claims, which are absolutely ridiculous.
But when I'm telling you now, I don't need to keep the temperature constant. As long as I keep the temperature...
The argument here was that Flatzoid said that Critical Think did not control for the temperature, and thus the values are completely random.
In the range of 15 to 30 degrees, then the scale is rated with that temperature. I've tested it that the scale will weigh the same in that temperature range. I don't need to control the temperature. That is the only control I need for temperature, is just keep it within a reasonable range.
And I completely agree. If you test your equipment and you can see that the changes are not measurable within the error or within the uncertainty, you can dismiss this variable as not contributing within the temperature range that you tested. I completely agree. This is how we do it in our physics lab and in the chemistry lab that is adjacent to our physics lab. We're working together with them. This is how we do it. 100% correct what Critical Think just said there.
Okay, so in case you didn't realize, you just didn't then do a repeatable experiment and therefore it's not science.
And that is complete bollocks. You have to keep all the variables constant, says Flatzoid. So, Flatzoid's claim is, didn't then do a repeatable experiment, you have to keep all the variables the same. And this is absolutely ridiculous. This is ludicrous even. I'm measuring the resistance of a wire, let's say at 20 degrees centigrade. If I do it again, it cannot be 20.001 degrees centigrade or the measurement would be wrong because, as we know, the resistivity of wires changes with temperature, and this is correct. But within this area, within this tiny temperature change, the change in conductivity or in resistivity, therefore, would be way, way, way smaller. It would be minuscule compared to the uncertainty my measurement apparatus has. This is absolutely a ridiculous standard of measurement, and it proves it provides evidence for one of Thun's laws of Flerf. I couldn't remember which it was, about flat earthers are pseudoscientists with their own evidence and science skeptics when assessing other evidence. There is no scientific measurement that could be this accurate. Absolutely impossible and very unpractical. If this is your standard, you could not measure anything. Go on to the next question. All the measurement values need to be the same.
Okay, I'm going to ask another one. Did you do that? Did you do multiple weights at Antarctica or just the ones?
Multiple, but you still didn't.
By not, he didn't mean multiple weights in the sense of one with 100 grams and one with 200 grams. He meant multiple measurements of the same weight, just to clarify here.
Answer my question.
And did
What
those
causes the prediction to be spot on?
Wait, and when you did those multiple measurements, did they all differ?
Of course, they're going to differ by a couple of hundreds of grams. Of course, they are. But
So
why is it
an invalid scientific experiment? Thank you very much.
No, you
cannot
understand.
You cannot repeat and get the same results because you cannot control your experiment. So therefore, not a valid scientific experiment.
Again, completely ridiculous. You did all of your measurements differ, so it is an invalid scientific experiment. You cannot repeat and get the same values. Completely false. Flatzoid he demands perfect, literally perfect to the dot measurements, which are completely unobtainable in real life. Flatzoid's standard of evidence is higher than any standard of evidence would reasonably be. Measurements only, we covered this in the beginning, need to agree within error to be able to say that they are the same. Let's go on to the next claim. Take this to a scientific institution, they would laugh at you, said Flatzoid to Critical Think.
If you had to take this, and I actually urge you to do this, please take this to a scientific, reputable education system and ask them, is this scientific? They're going to laugh at you because they're going to say, first of all, you didn't follow any science. You didn't control any variables. You just hand-waved dismissing everything that shows you don't have data for anything, and you're just making correlation. So therefore, they're going to tell you it's pseudoscience.
This assessment, of course, is completely wrong. Being a scientist myself, I think it is fair to call myself a scientist, even though I still haven't gotten a peer-reviewed paper yet. I promise we're working on it. It's just things keep happening. Regardless, if that doesn't count, I would be happy to ask one of my friends that are now in their PhDs and have peer-reviewed scientific papers to look over the data of Critical Think or to tell me if this overall statement, what Flatzoid is doing here, is correct. And I promise you the answer would be no. As a matter of fact, Flatzoid, you would be laughed at. The issue here is, why do you want us to go to a reputable institution? You're not going to care afterward. You don't care what scientific institutions say. If they disagreed with you, you'd just say, well, they obviously don't know. You did that with me when you said that I don't get entropy despite me having a degree within the relevant field and having taught this on a low level. But you said that I don't have an idea. The hubris you have to have, the ego that is involved here is ridiculous. You don't believe scientists, why do you want us to go there? And if we got there, they'd say that this is a completely fine measurement, because it is. The next claim. Oh yeah, that's my favorite. You need to go to Antarctica again, says Flatzoid to Critical Think. We here?
Okay, then I got another one for you. Are you going to go again to Antarctica to make the repeatable thing and see if it gives the same results?
Oh, maybe I will one day. But why do I need to do that? Because I go many places the same over and over again and repeated this experiment many times. Why do I need specifically to go to Antarctica?
Because that's called repeatable experimentation.
So Flatzoid demands that Critical Think goes there again which again is completely ridiculous. So first of all, repeatable just means that he has published enough information that someone could repeat it. He doesn't necessarily need to do it himself. Flatzoid, actually, why don't you go there and do it? It is also repeatable if you did it, and that way it's more trusting if another person does it, actually. This is how science works. You get another person to do the same thing you did by only giving them the necessary information so that they can check if it is reasonable in terms of results. You obviously don't know how that works because you've never done science. Why should he need to go there himself? Anyone can do that, provided they use similarly accurate equipment and the variables are within reason the same. The next claim. All variables need to be taken into account. This is a variation of the first point we raised here.
By 0.5%.
Sorry, I didn't
the
run it back here.
So if they were significant, I accounted for.
How many more? Not count. Okay, it's minuscule. Can temperature change? Even if it's minuscule, it can change their experiment results.
Not within the uncertainty of your measurement device. Or only within the uncertainty of the measurement device. I meant not above.
Yes.
Okay. And humidity does the same. Moving the scale does the same. If it's not calibrated, it does the same. Magnetic field does the same. How many more variables do I have to account for that is not accounted for?
You don't have to account for any of them if you can dismiss them previously during a process, by the way.
In your not experiment.
So they're all accounted for. I've already told you many times. I'm going to repeat again. They are all accounted for because they are insignificant. So
and I agree.
They were significant, I would not get the result. I would not get the correlation. I would know that there is something wrong with my experiment because the results do not match exactly within measurement error. I would know that I've missed out on a variable if it does not match. I've got the correlation. How do you explain that random things like temperature, pressure, etc., can produce an exact result? How does that happen? Magic again. You like magic, don't you?
I'm gonna teach you some more things.
You couldn't teach anyone anything.
I got one spoon here. Now imagine this spoon changes the scale on the weight on the scale by 0.5%.
But this would be significant. 0.5% in terms of a high precision scale is a significant change. What you need to say, the spoon changes the weight by a femtogram. No one cares. You could add hundreds of spoons. It would not be relevant. And this is the point that critical think is trying to make, that completely goes beyond Flatzoid. Flatzoid argues that you need to take all variables into account, which is ridiculous. Just make a perfect snapshot of the universe every time you measure things. How about that, Flatzoid? How about you measure every temperature of every room in the building, because there could be airflow due to temperature changes. You would need to have perfectly climate controlled, literally perfectly climate controlled buildings when you do scientific experiments. This is such an unreasonably high standard. No, not a single experiment could have been carried out in the history of mankind. Absolutely a joke. And accounting the error after the measurements is fudging the numbers. The last claim here, thankfully.
I don't understand what you're asking.
Do you account the errors after or before the experiment?
The errors are done by an error analysis, by taking readings over many measurements.
So afterwards?
You don't know what the error is going to be before. You have an idea, but you don't know exactly.
Which is completely correct, by the way.
Okay, so afterwards. So in other words, I needed to fit my results, so therefore let me waggle it and make it fit my results.
So Flatzoid is accusing every scientist here of just fudging the numbers with the error analysis afterward. Completely ridiculous. The error actually, in a lot of cases, depends on the value. I have it here from a Fluke multimeter. We use this at university, and a lot of universities use them. When you measure DC voltage, and for example, you measure in the range of 600 millivolts, the resolution that you can get is 0.1 millivolt. You cannot make a statement more exact than that, with an accuracy of plus minus 0.15% plus 2 digits. The 2 digits meaning 2 of the resolution here. So It would be 15% of the value plus 2 digits, and this would be the uncertainty plus minus, right? Of course, Flatzoid wouldn't know that because he's never ever done an error calculation in his life, yet he accuses an engineer of doing it completely wrong. Absolutely ridiculous, bringing me to my final slide. Flatzoid. I give you measurement data, 6 values. You find out the uncertainty based on this table here. You do an error analysis and you tell me about the data. Do the values agree with each other? Can they come from the same source? This is a question I pose directly to you, and I know that you are not going to do it, either fairly because you don't watch my video, which I suppose is fair, or because you have no idea how to do an error analysis. And with that, I would like to leave it. Thank you everyone so much for watching. I hope you enjoyed it. If you did, maybe consider leaving a like, and if you enjoyed it a lot, considering subscribing. And with that, I'm out. Until the next time, goodbye.